Hello, welcome back. Today we're going to talk about, or in this video we're going to talk about one-dimensional uniform acceleration or uniformly accelerated motion. In physics, when we say something is uniform, it means it's constant. So if there's a problem about uniform motion, something in there is constant, right? In this case, we're going to talk about motion where acceleration is constant. This is going to be a really big family of scenarios for us. And even things where it's not really constant, a lot of times we can either pretend it is, or you can break it up into portions where it is. So uniform acceleration is a really big scenario for us, and we will really work through it in gory detail and develop some algebraic equations. And then once we have those equations, they will be the real workhorse for maybe a full month of this course. We will use these. We're eventually going to have 3 equations. We're going to use them over and over and over and over. And they are going to really be the main tools that we use to solve problems. And okay. All right, so uniformly accelerated motion, or uniform acceleration, means motion where the acceleration is constant. It can be positive, it can be negative, it could be 0. That would be a constant. That's not a very interesting case, but we can handle it all in one go. Now, when I do my derivations of these things, I'm going to draw things with positive numbers, assuming the acceleration is a positive constant, just to draw pictures. But the formulas that I get would be the same, and you could go through it again, handling the negative case, and it would all work out. So you have to, I'm not going to do that on the board, but it would be there if you want to. Okay, so we're going to do this, and then we're going to also need the equation of a line. So in math class, a line is often described with an equation: y equals mx plus b. Everybody remembers that. Y equals mx plus b. What's y? What's b? Okay. We need to modify this, change the lettering so that it refers to things that we've been talking about, so that it's useful for us. So what this really is, this is only correct or appropriate if you have a graph where the vertical part is labeled with y, and so that would be the dependent variable, and the independent variable is labeled with an x, and then you would have a line, something like that. M is the slope, and B is it's called the y-intercept. Basically, when the independent variable is 0, how high is the graph? Okay. So hopefully that's all piece of cake, super easy for you. Y equals mx plus b. We have to understand how to modify that. So what we're going to do is assume that acceleration is constant. And then let's think about that. If acceleration is constant, I can also use the fact that I know how to represent acceleration in a velocity versus time graph. So let me remind you of that. So the acceleration is the slope of velocity versus time. Acceleration is the slope of velocity versus time. If the acceleration is constant, then that means the slope of velocity versus time is constant. And we know from math class that when you have a curve whose slope is always constant, it's a line. So that means that uniform acceleration is the same as the velocity versus time graph is a line. The slope is the acceleration. Okay. Uniform acceleration means acceleration is constant, but acceleration is the slope of velocity versus time. Therefore, velocity versus time graph needs to be a linear graph, like that. Very good. Well, shoot. This graph looks a whole lot like this graph, but we need to change the spelling. So here the independent variable was x. But in physics, we like to think of time as being the independent variable. So we're going to have the equation for a line, but everywhere we have x, we're going to swap it out for time. Too hard. And the dependent variable over here was y. So here, the dependent variable is v. So we just change the spelling in an appropriate way. Over here, the slope was m. For our equation, the slope is going to be a, the constant acceleration. So we're almost done. So let's think about that. Let me write it out. So I would say if I'm translating the math equation into physics variables, I would say that v equals m. So sorry, y becomes v, m becomes acceleration, x becomes t for time, plus b. Okay? B. Well, you could do that, but we don't need to because we have a physical intuition or physical interpretation for this graph. Remember, b was the height of the graph when the independent variable was 0. So it's really how high the graph starts when it hits this axis. For us, that would be the height of the graph when time is 0. What does that mean? Well, that would be the velocity when time is 0. So instead of calling this b, which doesn't give us a clue as to what it means, this height right here would be the initial velocity. So sometimes you put a subscript 0 for 0 time. Sometimes, I think in many regions physics books, they put an I there. Subscript I for initial. That would be the height of the velocity time graph when time is 0. Personally, I prefer 0 because I'm lazy and it's faster to write a 0 than an I. It's that simple. So I will write everything with a 0, but if you prefer I, it is totally fine. It's just whatever sticks in your mind, really. So instead of writing B, because I would never remember what that is, let's write V initial. That's a good equation. We will use that a lot. This is fine. I will just tell you, I prefer to write it with the constant term first and the linear term, the time term second. I don't know why. So I will write this. I will just swap this around. It's a cosmetic change. And write this as V initial plus the acceleration times the time. I'm going to box that in. And that's going to be a big equation for us. So I'm going to go ahead and call this kinematic equation could call it something else, Bob or Fred, but that no one would remember. So, kinematic equation number 1. On a test, I usually give a couple key formulas. I would give this to you because I wouldn't want someone to understand everything and just, I don't know, blank out and be stuck. That being said, you need to know this. When we work examples together and we're kind of laying a path through, it's sort of like solving a maze. You have to lay a path through a problem to go from the information you're at the start to the answer you want at the end. We're going to plan paths. And before we dive into numbers, what we're going to do is say, oh, start with this. Use kinematic equation 1 to find something else. And then maybe use a kinematic equation 2, which I'm going to describe in a minute. And we're going to use these, I want to use a common language, equations 1, 2, and 3, eventually, to help us strategize and plan how we will solve problems. So that is kinematic equation number 1. It describes the velocity as a function. So velocity as a function of time when acceleration is constant. It's really just the equation of a line, but you know, we've been going through a whole bunch of videos. There's a whole bunch of baggage that you have to kind of learn how to carry to use this equation. All right. I'm going to keep going. I'm going to introduce the other kinematic equations here. And you know what? Take that back. I'm going to stop the video now, and I will put the second kinematic equation in the next video. And that way it's segmented so that it's easier to view. And then after we get through all that, we'll start practicing problems after we have all the equations. Okay. See you next time.